Hi everyone, my name is Mauricio Gamonal, and I am a grad student at Penn State. And I'd like to share with you, with the people of Cosmology from home, some of the preliminary results on primordial cosmology that we have obtained in this project with my advisor, Eugenio Bianchi. This is a work in progress, but I still like to share some of these ideas. As a motivation, I'd like to point out that although it is very successful, general relativity, we know that GR is not a complete theory, since it does not properly describe quantum mechanical phenomena that we actually expect to see, especially at the Planck scale. This is a scale characterized by the speed of light, g Newton, and most importantly, h bar, which doesn't appear in general relativity. Many ideas for a theory of quantum gravity, of course, have been proposed in the past, such as loop quantum gravity, spin forms, asymptotic safe gravity, string theory, among many others. But it's still an open question in modern science. However, in particular, there is a natural lab where we expect that semi-classical effects are relevant, and that is, of course, the primordial epoch of the universe. In particular, within the context of cosmic inflation, which gives a very good description of the universe that we observe, and in particular the fluctuations of the anisotropies of the cosmic microwave background. In that sense, we are in particular interested in purely gravitational models, such as, for example, R² inflation. And we see in the plot on the right that these kind of models, they provide good fits to the Planck data for the constraints given by Planck in a couple of years ago. And those models, purely gravitational models of inflation, they don't require an inflaton field. They don't require a scalar field. They're purely gravity. Pure gravity just provides the enough amount of information to produce inflation. So we're focused on that because from these observations, we wonder, how can we consistently push the limits of general relativity? How can we extend this theory in a consistently way? And there are many arguments that have appeared in the past towards the idea to include new quantities on the action of gravity. There are arguments coming from the fact that we can add terms that are allowed by the symmetries of general relativity, like diff invariance. Arguments from the normalization techniques that appeared in the 70s and the 60s. And also arguments coming from the fact that gravity, the gravitational interaction, can be treated as an effective field theory. All of these ideas have been around for a couple of years, and all of them points towards the logic that we can expand the action in terms of the derivatives of the metric, and a systematic expansion. And we can see here, for example, that if we start with this organizational principle that we call it, with zero derivatives that will give the cosmological constant, two derivatives that will give us standard general relativity, and a new contribution coming from terms that are up to four derivatives with respect to the metric. These are the kind of models we are interested in, particular in the context of inflation. We can use some tricks and techniques to reduce and simplify this. In particular, we can use the Cosmonet Theorem that tells us that this term in red in 4 dimensions is a surface term. It doesn't contribute to the equation of motion. We also can use the Weyl tensor, which is defined as it is in the slide, because the Weyl-squared, Weyl, can be rewritten as R², Ricci square, and Riemann square. So this combination of the most general 4-ordered terms can be rewritten in a very clear way here on the blue equation down as a combination of R² and another term, Weyl-squared. That is the action we are gonna consider for this project. We can see that this has been addressed in the past. The R² term was addressed by Starobinsky to study the cosmological consequences of including that term, and the Weyl-squared have been considered in a way for other other authors like Steven Weinberg in 2008 and Anselmi et al. In 2020, but with some specific differences that we can address. What are these differences, and what is the new thing we are bringing into the table? From Weinberg, we are not including any additional degrees of freedom. We are taking this coupling alpha and beta as constants. They are not functions of any other scalar field. And from Anselmi, Bianchi, and Piva, we are not invoking purely virtual particles to describe the physics of this model. We are going to remain on the geometric framework, and we are going to be as conservative as possible and to try to extend the theory of general relativity and apply it to the inflationary phase. So the contribution is, for us, what we did was mainly developing and implementing a systematic method to deal with these higher order time derivatives that will appear as a consequence of including the Weyl-squared term, and describe them as effective equations that can be obtained order by order in beta. With this, we can isolate the contributions to cosmological observables, such as the two-point correlation functions on the power spectrum, and then get corrections to them for the primordial fluctuations. Before discussing the fluctuations, we can set the background that we are going to consider. The background is just Friedman, Lemaitre, Robertson, Walker, no cosmological constant, and a especially flat universe. And we see that, and I want to emphasize here that one of the main aspects of this approach is that we are going to remain in the geometric framework. We are not working with the scalar field as the inflaton and any other matter field. This is pure gravity acting on itself, producing inflation. And we can see that since the Weyl tensor vanishes for the Friedman, Lemaitre, Robertson, Walker metric, there's no contributions from the beta term, the Weyl-squared term, and all the contributions come from the R², which is what we know as the Starobinsky model of inflation. And it works perfectly fine in the geometric approximation, as we can see here in the plot on the right, that this model, the Friedman equations that appear here, when we solve it, it gives an inflationary phase. And not only that, it gives also a slow roll phase, a slow roll inflation phase. This, of course, has been discussed in the past using the fact that Starobinsky inflation can be rewritten as a scalar field with a very specific potential. We will see that we cannot use that trick anymore if we include the Weyl-squared term, and that's the main reason why we are using the geometric framework, and we are going to remain there for all the discussion. Just to make a consistency check, we can discuss the cosmological perturbations for the case of Starobinsky inflation. That means we are going to neglect the effect of beta and the Weyl-squared term, and we use the standard procedure, that is making cosmological fluctuations on the metric. We are going to take the quadratic action, we fix the gauge, we are going to use moving gauge, and we set the constraints, Hamiltonian constraints. And when we have done all of that, we will remain with the physical degrees of freedom of the theory, and they are one scalar curvature perturbations that will describe the scalar tensor modes, and the scalar and the tensor modes that are the two other degrees of freedom that appear in the theory. Once we write the quadratic action, we can use the standard procedure of Mukhanov-Sasaki variables. We can obtain the Mukhanov-Sasaki variables, and then using the standard quantization in order to compute the two-point correlation functions of these operators. And from there, we can read the power spectrum for scalar and tensor modes. This gives us the standard predictions for Starobinsky inflation. This is also something that we already knew, and therefore it's a consistency check, because the formalism, the geometric formalism that we are using is totally consistent with what is in the literature. However, when we consider the Weyl-squared term, when beta is no longer 0, new things appears. And the new thing that appears is this extra term in red that is in the quadratic action, for example, for the tensor modes. This term, as you can see, is an acceleration term. It's an x double dot in the action, basically. So when we take the equation of motion, we will obtain something like a fourth order derivative. And therefore, even at the classical level, it's going to be pathological if we treat it as it is. Like, and even more problematic will be at the quantum level. So the question here is, how can we extract a physically relevant solution from these kind of actions? And it turns out there is a method to do this. And there's a very specific example that I would like to point out. This is called the Abraham-Lorentz force. It's classical electrodynamics. We have a charged particle that is accelerated. So therefore, from Larmore's formula, we can derive the self-force for this particle, and we'll see that this self-force goes as x triple dot in the equations of motion. That is problematic. It has many pathological features, and therefore some people think of it as an unphysical theory. However, Landau and Lifshitz, they treated this in a very consistent way, which is sometimes called reduction of order, which is basically solving the equation of motion at 0 order, and then reintroduce this into the original equation in order to obtain an effective force that could read some of the corrections coming from this self-force. The funny thing is that this equation have been used to predict some measurements in the lab, and it seems that there is some evidence, experimental evidence, that the Lorentz force is not enough to describe these radiation processes, and the Landau-Lifshitz process, the Landau-Lifshitz equation, this reduced equation, actually is a very good fit to what is observed in the lab. So maybe we can use the same logic. Maybe we can use the same logic in cosmology and use reduction of order to implement a systematic method and solve for the predictions for these primordial fluctuations. As a more precise example, we can read from this harmonic oscillator, which has an acceleration term. We can see here that we use the same scheme. We solve for the 0 order solution. We can compare it with the exact solution, and the comparison gives us very good results when the initial conditions are close to be stable ones, as opposed to an arbitrary solutions. This analysis also gives an intuition that the parameter beta has to be negative, because for positive values there's an instability that gives us runaway solutions that we cannot get rid of it. So this imposes the condition that beta has to be negative, which is also a condition that has appeared in other parts of the literature. So this is consistent with what has been discussed before. So if we use this technique of reduction of order, and we use it in the quadratic action of gravity, of the tensor modes in particular, we will obtain some slightly different things as we had before, some specific corrections, as we can see in the plot. And these corrections are parameterized by the ratio beta over alpha, like the comparison between the two scales, between the Weyl-squared term and the alpha that comes with the R² term. However, we can treat this systematically. We can solve for this, and we can actually obtain the corrections to the power spectrum. There are a lot of details in between, of course, but I want to just show up and show what are the main corrections, what are the main differences from what we had before. These are the power spectrum evaluated at the pivot scale for tensor and scalar modes. The first two lines are for scalar modes. There's no contribution, there's no corrections for them. But for the tensor modes, we see a correction coming from this Weyl-squared term. And you can see in front of it, the amplitude of this power spectrum. It appears h bar, g Newton, and c cube, which is the Planck length square. And alpha is also has units of length square, units of area. So in a way, this is, of course, a signature of a perturbative quantum gravitational effect that it's present in the power spectrum, in the amplitude of the power spectrum of these primordial fluctuations. And in particular, this correction that we see, we saw that beta has to be negative. So this correction coming from Weyl-squared tend to reduce the power of tensor modes, and also for the tensor-to-scalar ratio, which is actually a very interesting aspect, because it can be tested, in particular, with the CMB stage 4, the next stage of CMB measurements. And it could be possible that the precision that we are going to get with the CMB stage 4 in a couple of years from now will give us a very good opportunity to test how good this model is. If it could be, this model could be ruled out, or we could support it, we don't know. But this approach goes in the direction of self-consistently treat this problem, the problem of expanding and extending the theory of general relativity in a self-consistent way. As conclusions, I can mention that therefore, it is clear that pure gravity plus these higher order curvature terms can trigger cosmic inflation. We also expect deviations from the Starobinsky model if we add the Weyl-squared term. There's no reason to not consider the Weyl-squared term if we already consider the R-squared term. So if we take R-squared, we have to take a Weyl-squared as well. And cosmological perturbations are studied under reduced D order. We can extract the physically relevant solutions, and we see there is a corrections. We see the deviations from Starobinsky inflation, and that's what we obtain. Thank you very much for all those who have watched the whole video, and see you later.